And then we'll share the screen. Okay, so here's the syllabus, and we're up here for on the 1st of September. Hard to believe. September's already here. So homework 1 is due today, and I promised to take a quick look at that. So let me do that in just a second, and then we're going to continue on chapter 2. All right, so let me get rid of that, and then let's go to homework. Let's see, homework. Here it is. And oh, that's the turn-in folder, I guess. 10 files. So this is. Okay. Yeah, I guess that's it. All right. I thought there was another one. Let me just make sure. Go back here. Hang on 1 second. No, that's it. Okay. All right. And I hope, let's make sure I have this all set up correctly. I think I did. So if we click on that. Yeah, okay, that is set up correctly. So that's good. So it's due Wednesday, the 1st. It should stay available for 1 week after this, but you'll be half off. So try and get it turned. So even if you only have it, 60% done, your money ahead to turn it in tonight instead of before 11:59 than you are instead of waiting sometime in the next week to try and turn it in where you already lose 50%. Okay, and then let's look at the homework. We'll talk about it real quick. All right, so I think I may have mentioned this briefly before, but just to go over it. So I went over the definition of legal labels, and that's in chapter 2. So if you go back over the slides, which should be on the web on Blackboard, you should see that. You can also find it in the book. A primitive is just a pre-built gate or element that the synthesizer can use and just use to create your net list. How many primitives are there in Verilog? Actually, I forget that, but you can Google that probably and find the answer. I don't know. They're not that many, surprisingly enough. What's a UDP? That's a user-defined primitive. You can, as a user, you can create your own user-defined primitives and add them. Although I've never done that with Vivado, I'm sure you can do it. There are some rules about how to make one. We're not going to do that in this course. So when I first started teaching this, I was a little more preoccupied with user-defined primitives than I am now. And probably I should just delete this question. But anyway, that's what that UDP is. And in the port list, the outputs must come first. Is this also true for modules? No, it's not. The outputs and inputs can be mixed all around for modules, but for a primitive, the outputs have to come first. Can you define a module inside another module? You guys should already know the answer to that. How many times can you instantiate a module? We've talked about that too. You can instantiate as many times as you have room and size of your program and your resulting chip or FPGA bit file. List all the logical operators in Verilog. That should be straightforward, and all the bitwise operators. You should do this. I do believe I'm not sure if I actually covered this in the lecture yet, but you should be able to find this in the book, or you can definitely Google this. These will all come up. There are some obscure ones. I don't care about the obscure ones. I really care about the main ones. So if you miss one or two, it's not the end of the world. You'll find out as you go through your learning of Verilog that when as soon as you think you have some aspect of Verilog fairly well understood, you will find that there's a whole bunch more things you never knew about. And that's how Verilog is. It is incredibly complicated, but you can get a lot done with just the basic information. All right, explain the difference between logical and bitwise operators. You should be able to do this. And remembering that for bit variables, there's no difference. Explain the difference between wire and register variables, at least give a few differences. So you should be able to do these things. I think we've covered all this pretty well. All right, I'm gonna stop with that. Are there Does anybody have any burning questions about the homework? Yes, no? Let's see, there's 6 things.
Now, all good.
All right, so 26, I think. Really? Yeah, maybe that, yeah, 26. It's on the back of the book. Okay. That's good. That's probably, yeah, that's interesting. I actually didn't think it was that many, but that's not a huge number if you think about it. And that's because you can do so much with just so few gates. Okay. All right, let me share the screen again. And I'm going to switch to, so we'll get rid of this. And so we'll get rid of that one. And then I'm going to do this one. Okay, so yeah, so turn in homework 1 by 11:59 tonight. Shouldn't take you long to do it, actually. Okay. So remember, I'm backing up a couple of slides because I wanted to just review this. So remember, we talked about wire and register. You should have a good concept. And so let's just review this because this is, you're going to use this a lot. There are other net types besides wire and register, but these are the main ones that we use these all the time. And the other ones are a little more obscure. Eventually we'll cover some of the other ones, but not to worry about it until later on. And let's see, I think we can put this here. All right, so a wire is just like it sounds. It's typically only used, well, it's related to combinational logic. Now it can be on the right side in the sequential block. That's fine. It just cannot be on the left side in a sequential block. So it can't be on the left-hand side of an equal or of a blocking or a non-blocking in assignment statement in an always block. And the data type wire is the only legal type on the left-hand side in a continuous assignment statement, of course, outside of always blocks, because continuous assignment statements don't show up inside always blocks. We have inside always blocks, we have sequential statements. Unless, of course, you're using an always block in a bastardized manner to actually create combinational logic and not sequential logic, in which case then you must define the left-hand sides as registers, but the synthesizer is smart enough to know that's not what you meant, and it will turn your defined registers into wires because that's what really they have to be. Registers in a real sequential block, they are the only legal net type on the left-hand side of the assignment statement, which can be blocking or non-blocking inside of an always block. It is not allowed to be used on the left-hand side of a continuous assignment statement outside of an always block. And the initial block, which is also a process block, which is used normally in test benches, but it can be used to initialize things when you're doing when you're creating a bit file for an FPGA. It is also the only legal type on the left-hand side. Okay, having said all that, so I just want to make sure. Does anybody have any questions about wire or register? Because these are really important concepts to get under your belt. Not hearing any questions, I will move on. Okay, and there are other data types besides these, but we really don't use those other types very often. Okay, now there are a whole bunch of sequential statements. If statements, case statements, for statements, repeat, while. There's a thing called a forever statement, but it's pretty much only used in test benches. There's an unnamed block statement. There's a forked and join statements. There's a wait statement. There's event trigger statements, delay statements, disable statements, and assign, deassign statements, and force release statements. We're not going to, most of these we're not going to use. We may use the wait statement. And obviously we will use if, case, for, and while. But there are a bunch of sequential statements we're never going to really encounter in this course, nor are we going to use. And some of them are pretty, kind of for the very high level power Verilog users. But I just wanted to throw that up there so you could see that there is a whole bunch of stuff, some of which we're not going to see. Okay, flip-flop, classic sequential device, which does make up as the memory storage element for all of our registers in all of our digital devices, all of our microprocessors. We create registers with flip-flops. That's, you know, our program counters, our stack pointers, all of our programmers model registers. They all typically are made up of some number of flip-flops. In the case of like the Freedom board, the KL25Z chip on that, that's an ARM M0 plus core, that uses all the registers are 32 bits. So there's 32 flip-flops set up for every register. And they're set up to be as high speed as they can, because that's really the rate limiting step for your maximum clock rates and whatnot. All right, so basic flip-flop. D flip-flop is our basic register type flip-flop, and it's an edge trigger device. The clock could be falling or rising. In this case, because there's no bubble, it's a rising edge. And usually it has both a Q and a Q prime not shown here. And it can be set up, yeah, it can be set up on a rising or falling edge. You model this in Verilog with an always block. And it looks something like this. This is, of course, as stripped down as you possibly can get. And notice we have in the sensitivity list, there is an edge signal, not a level signal. And notice in the body of the always block, we use a non-blocking assignment. Probably wouldn't have mattered, since there's only one statement here. Whether it's blocking or non-blocking would probably not really have mattered. But to be consistent, normally when we're actually making sequential stuff, not always, but almost always, we use non-blocking assignment statements. Okay. Now here's a transparent latch. The whole way this latch works is, as long as the gate is open, D is immediately propagated through to Q. So if D changes, Q will follow it with a small propagation or transport or inertial delay. Propagation delay, inertial delay mean the same thing essentially. And so when G is inactive, in this case inactive low, then D has no effect on the latch's state. Whatever the last value of Q is preserved until the gate opens up again and D changes. And here's what the code looks like. Note, these are level signals, not edge signals. So level signals can be used for sequential devices. It doesn't have to represent a bastardized use. And this is G or D. Remember, you can also just put a comma there. And that's the syntax I prefer, G comma D. But or is okay in this sensitivity list. Notice it's not the vertical bar or, it's just a lowercase English word or, and it's just notation. All right, and then within the always block, we have an if statement. If the gate is true, which means active high in this case, then Q is assigned the result of D. And notice they used a non-blocking statement here, indicating that they really did intend this to turn out to be a sequential device. So this is a sequential device, even though it doesn't have a clock per se, but it does have memory. And so if Q is inactive, then this device will retain. If the gate is inactive low, this transparent latch will retain the last value of Q and continue to output. So it is effectively a storage device, which means it is sequential. All right. Why does D have to be in the sensitivity list? Well, obviously, if the gate is active high, so the gate's open, Q has to follow D. So D has to be in this list to cause this to change with a change in D. So with a change in G, it'll execute. With a change in D, it'll execute. But if G is inactive low, D will have no effect. But if G is active high, then Q will follow D. So you have to execute it with a change in G or a change in D. Okay,
Dr. Martin, I have a
yes,
question, please.
go ahead.
You said there's edge level, and what was the second one?
Okay, so the yeah, okay, so let me go back. So so we talk about so this is so we have edge signals, which you
Yes.
can see here, pause edge clock,
Okay.
and we have level signals, which you see here because there's no edge designation.
Okay, so this one is level signal.
So remember, in the sensitivity list in Vivado, you can't mix edge signals and level signals.
Yes.
So both of these then are level signals. So that's legal. And it actually is intended not to be combinational logic being used in this bastardized sense we've talked about, but it is actually intended to result in a latch, which is a sequential device because it has memory. And what it remembers is the last value of Q when the gate closes.
So to figure out which one is which, if I say it's an edge signal, it's only associated with a clock, or
Well,
how do you know like that's an edge signal?
Well, so what's the difference between a level signal and an edge signal? And so let me turn this on, and we'll take a quick look here. And so let's see. Okay, so so if you have a signal, it could be a clock, it could be anything. It could be some kind of trigger. So a level signal means this whole part of the signal is active. An edge signal means only either this part or this part are active. So for instance, if you had an edge signal and it looked like this, then this would be the only active part of the signal. All this wouldn't do anything. Now, typically a clock is going to have some, repeating square waves like this. Usually square waves, but not always. Actually, in real worlds, a lot of the clocks, because they're so fast, and so they're not, they may not be perfect square waves, but it's nice to have a nice sharp edge here to trigger on. And the reason we use edge signals is because if we let the transitions take place anytime during the active high part of the signal, then you have a fairly large block of time where the transition might occur, and you're not exactly sure where in there it'll occur. But if you have edge signals, it's always going to occur very close to that edge, minus, plus the small amount of inertial delay. So edge signals are important to keep everything synchronized in a big system. But there are some applications where we use level signals, and a transparent latch is one of those examples. Okay.
Okay, thank you very much.
Oops, why did that do that? Okay. So does that answer your question, Ahmed?
Yes, sir. Yes, thank you very much.
Okay. All right. So here's a D flip-flop with an asynchronous clear. So what do we mean by an asynchronous clear? We mean a clear that does not synchronize with the clock. So anytime the clear happens, then it's going to cause the flip-flop to go into a clear state, plus some small inertial delay. So since the asynchronous, and we usually name these signals clear if it's active high, clear not if it's active low, just to try and make life easier. So if you see CLRN, that means clear not. So you can bet it's supposed to have a bubble. If you see just CLR, generally that means it's an active high clear. And we try and be consistent with that because life's confusing enough without adding to the confusion. All right, so here's a clock, rising edge or falling edge clock, or pause edge or neg edge. What would the clock
Rising
be?
edge because there's no bubble.
Yeah, so it's pause edge. Okay, and then is this clear signal an edge signal or no?
That's a level signal.
Well, okay, so let's look. Notice in the sensitivity list, we have to give it an edge, because if we don't, we'll mix level signals and edge signals in the same sensitivity list, which Vivado won't let you do. So you have to make it an edge signal. Now, we don't put a caret on here because it's not a clock, but it is an edge signal. And the reason it's an edge signal is because this execution occurs on only the negative edge. When the positive edge occurs, this does not change the flip-flop at all. It only changes when the signal is inactive and it suddenly becomes active. And when that happens, that's effectively an edge signal. When you get the positive edge of the signal, you're going from having the clear asserted to having it deasserted. And as you know, nothing happens until the next active edge of the clock then. Just because you deassert the clear doesn't do anything to the flip-flop directly. It has to wait on the next active clock, and then it responds to D. And if you remember logic design, I asked you that on a test. You know, if we, you know, not everybody got an asynchronous clear or an asynchronous set, but if we did, then you knew that just because the signal went from active to inactive didn't mean anything particularly changed. It just means now the flip-flop can respond to the clock and the D input. All right, notice the D is not in the sensitivity list here. And it's not in the sensitivity list because you don't want this to execute whenever D changes. You only want it to execute either on the asynchronous clear when it goes from inactive high to active low, or on the positive edge of the clock. Now, if the clock changes and this executes, the first thing it's going to do is test the clear signal. And if the bitwise inverse of the clear not, so if clear is active low, this will be true. And Q will be set to 0. And the else statement will not be evaluated. If clear not is high, which means it's deasserted, then this inverse will be false, and we'll go to the else statement and we'll set Q equal to D. So since the asynchronous clear not signal overrides clock, clear not is tested first and the flip-flop is cleared if clear not is 0. So as long as clear not stays asserted active low and the positive clock edges come and go, every time the positive clock edge is hit, it's going to test it. Oops, our clear is still asserted, so we'll keep Q at 0 and we're not going to even evaluate D. But when this is finally deasserted, well, nothing's going to this is not going to execute at that moment, because all you've done is there's not it's the positive edge of clear not doesn't trigger this execution. So you wait for the next positive edge of the clock, and when that occurs, this if statement will be false, and we will then set Q equal to D. So you should look at this until this makes perfect sense to you. Again, only edge signals in the sensitivity list because you can't mix them. Now, I think probably in some synthesizers you can mix them, but you can in Vivado. I don't know for sure about Cadence when you're making chips, but this is true here. Okay, if else statements. So we typically have if condition and then statements. Now, if we only have one statement, like here, we just write it. Notice the semicolon is at the end of this. So you could put it all on one line if you want, or you can have it on 2 lines because white space doesn't matter. But if you wanted to have multiple statements, you would have to put a begin and an end. We don't have curly brackets in Verilog. We use begin and end statements to create essentially our curly brackets when we want them. So if you can only do one statement, it's fine. You just write that statement just like you do in C. But if you have more statements, then instead of using curly braces, you do begin all your statements and then an end. And then you have else, begin, and end, or whatever, however many statements you have down here. All right, a more general form of this is if, else if, and else. Now, remember, these if-else statements have to appear in procedural blocks. Just when we went back and looked at this, all these statements are sequential. They have to be in an always block or an initial block or whatever. All these have to be in these sequential blocks. And you can't have if statements outside of an always block. You can't have case statements outside of an always block. You can't have for statements outside of an always block. You can't have while statements outside of an always block. Or any of these other things can't be outside of always blocks. Okay, so so these have to be in always blocks, and the more general form of it is if, else if, and else. Remember, the first time you encounter one that's true, none of the other following statements are evaluated. They're not even looked at. And if you again, and you use begin and end if you have more statements, if you have a whole bunch of sequential statements in here. All right, so D flip-flop with a synchronous clear. Now, let's talk about this for a second. So if your clear is going to be synchronous, how are you going to handle that? So does the clear appear in the sensitivity list? Yes, no?
It should be in the sensitivity list.
No, not in the sensitivity list. That would
Okay.
make it asynchronous. So in this case, you only have the clock because since the clear is synchronous, it's going to occur on the clock edge. That's what it means to be a synchronous clear. So you only check the clear on each clock edge. And if it happens to be inactive then, but then it becomes active just after that, you have to wait till the next active clock edge to check it again. So there'll be a delayed effect. And it looks something like this. It's just got a gate on the D input, and it basically forces the input to be 0 unless the clear is inactive, which means in this case that it's 0, but the bubble makes it 1. And so that gates D on through, and then it just waits on the clock. Here we have if and then else. So if the clear is inactive, then D is assigned to Q. Otherwise, if the clear is active, then 0 is assigned to Q. Does this make sense? Any questions? All right. So you can think of these nested if and else if statements just like an SM chart, just like sequential design. And that's why they show up in sequential blocks. That's why you can't use them outside of sequential blocks, because they basically follow this sort of logic. Now, turns out we can use something outside of always blocks that's similar to this, and that is the question mark colon statement. And we'll talk about that later, which is essentially a conditional assignment statement. But if you want to use an if else ifs and else, you have to use you have to put these in an always block. And you can see each of these could sort of match this process here. But this would change the link path through the block, but it's just one block. Okay, JK flip-flop with a direct set and a reset. So here you have a reset and a set. Reset not, set not. So they have bubbles because they're active low. Clock, falling edge clock or neg edge clock. J and K as inputs and Q not and Q as outputs. And remember, almost all of our flip-flops are going to have Q and Q prime or Q and Q not, which is why when you did your logic design problem, you didn't have to count your four inverters on your inputs, because you normally do have all the inputs. Normally you do have the Q and Q not available because it comes out of a register typically. All right, well, anyway, might come out of the gate, in which case you might need an inverter. All right, so what's this code going to look like? So here we go, module, JK flip-flop. We have a set not, a reset not, a JK, a clock, a Q, and a Q not. Inputs, set, reset, JK, clock. Outputs, Q and Q not. We have an internal register, and that internal register is required because we're going to make this the left-hand side in our always block. But then we're going to just do assignment statements outside of the always block to drive Q and Q not. The register will be the right-hand side, that's legal, but these, so what type of net is, say, K? What type of net is Q not? Somebody tell me.
Ask it again.
Yeah. So is J? Well, okay. Is Q not a register or a wire? It's not specified here.
It'd be a wire.
It has to be a wire. First off, because you didn't say. When you don't say, it's always a wire by default. But notice it shows up as the left-hand side of a continuous assignment statement outside of an always block, which means it's got to be a wire. Can't be a register here. Inside this always block, the left-hand side, Q int, and Q int. What do those have to be?
Reg.
They have to be reg because they're the left-hand side inside an always block. So that's why you have to define this as a register. And basically, I mean, this sounds goofy, but when you define this register, you've created a flip-flop. Okay, so notice here we have for the reset and the set, it only takes 8 nanoseconds for inertial delay, but to change the flip-flop with with J and K, we have an inertial delay of 10 nanoseconds. Probably not unusual. The reset and set are usually a little faster. All right. And notice this, the formula for this is just the next value of Q is just the present value of Q prime ANDed with J, or K prime ANDed with Q. So that's how a JK flip-flop works. That's the characteristic equation for the next state, Q plus. We covered this in logic design. All right, wait statements. So a wait statement is something you can use in an always block. And basically the always block will execute the sequential statements until a wait statement is encountered. And then it waits on the wait statement to be satisfied before it continues execution. So it basically blocks execution until the wait statement is satisfied. So the wait statement is used as a level sensitive event control within your always block. And the general syntax is wait and then a Boolean expression. The Boolean expression is evaluated. If it's false, then the execution just stays right there until that Boolean expression becomes true. If it's initially true when it checks it, then it just immediately executes. And so this would be, this is the right line. So the always block executes. They didn't put it, there's no sensitivity list here because it's going to execute based on this wait statement. So it sits here as long as right is false, which means in this case inactive low. And then when it becomes active high, then it sets memory equal to data in, but then it has to sit here until it's low. When it's low, when it goes back low, then it lets the current value inside the memory to appear on the data out port. But it doesn't let that happen until it first puts new data in, and then the right line goes back low. So this is a construct you might encounter somewhat frequently when you're trying to write a memory location, say. And notice there's no clock driving this. There's no sensitivity list. So this always block is always essentially executing based on the value of the right line. The right line's high, then it's going to be sitting here. The right line's low, then it's going to be, well, then it'll fall through here and wait here. If it's high, it'll fall through here. It'll execute this and then go here and wait. And it just kind of skips back and forth between these two states. All right, so it's good to kind of think about this. Make sure you kind of understand how that works. Okay, so the three golden rules for always with combinational logic. Okay, now this is the bastardized use. Okay, this is when we're going to use an always block, not to make sequential logic involving memory, but to make combinational logic, because apparently we were too lazy to do it with assignment statements and the colon question mark construct. So all inputs to the design must appear in the sensitivity list, and all variables must be assigned under all conditions. So those are the two golden rules. There must be a third one. I guess not. We should change this. I wonder if I deleted one. Well, anyway, two golden rules. If you don't follow these rules, then you won't get combinational logic. You'll get something that's screwed up. And usually that makes an unintended latch is what happens. All right. And let's see. So that's that. So we'll jump from here to the next one. Okay, and then now we're going to talk about some delays, compilation, simulation, synthesis of Verilog code, data types and operators. So we'll do that. So two types of Verilog delays. So now, is this important for synthesis, or is this important for simulation, or both?
Simulation.
So it's primarily for simulation, because you don't get to tell the you don't get to tell the quantum mechanics how to behave. Quantum mechanics behaves as it wants based on the hardware. So whatever the hardware is, however that's determined, that's gonna determine your inertial delays. Your transport delays you might have some influence over, because that has to do with placing, mapping, and routing. And if you route a long path, your transport delay is going to be greater. If you route a smaller path, it's going to be less. Usually the router is automatic and works on its own, but you may be able to move things around and force some changes in how these transport delays work out. We won't do that in this course. That's, pretty high level stuff. But if you're making a really, if you're trying to force an FPGA or you're making an integrated circuit, then you can move things around in such a way that you can optimize some of your clock lines or signal lines that are causing your problems in getting closure in your timing. And because speed is a big deal in the digital world, and slow devices tend to get less market share and cost and are cheaper, and fast devices can command a higher price point and usually get more of a market share, unless they're outrageously expensive. But speed is always an important thing. So you're always trying to achieve some speed objective. Also, you don't want timing problems on your chip to cause errors in how it performs. So that could happen if a signal gets someplace too late to get properly latched in, because your routed pathway was too long. Remember, when we're talking, when we're down into the nanoseconds for gates and whatnot, the speed of light travels about a foot in a nanosecond. So a nanosecond is a measurable length when it comes to even an integrated circuit. It's fractions of a nanosecond, but significant fractions. If you had a route path that was 6 inches long, that could be 0.5 nanoseconds, which, at really high clock speeds could make the difference between getting latched or not latched. So you do have to think about these things. Okay, so the answer then is we worry about these primarily. We worry about these primarily in our simulation, but our simulation is hopefully designed to reflect our actual hardware. So we're not just going to pull random values out of thin air and assign them for inertial delays and transport delays. We're gonna look at our intended hardware and what the actual performance of our intended hardware and the gates we've designed, with the feature size, the operating voltage, the parasitic capacitance, and all the other features that we have to consider. What is the actual performance of say an AND gate? What's the actual performance of an OR gate or a NAND gate or a NOR gate? And that's one of the reasons why we tend to make them all NAND gates or all NOR gates, as opposed to trying to mix things up. So we have some consistency. But in any event, these delays are basically defined by the hardware, but we try and model that by picking good values to give us, and we might make them a little more generous than the reality, just so we can have a margin of safety in our maximum clock speed. And so these values we put in, they are used in simulation. That's the key. So inertia, resistance to motion, action, or change. So this is how long it takes a gate to change from one state to another. So when we talk about inertial delay, we're talking about this changing one state. It's typically the same as propagation delay. And when we write it, we write #5, D is assigned A ANDed with B. In this case, we're using logic land, but if it's just a bit, same as bitwise. And if we have a little glitch in one of these signals that's shorter than our overall propagation delay, then D, when we simulate this, D won't change at all. In the real world, D might flicker a little bit, but it probably won't give us enough of a spike to actually cause an error. Okay. So this is what an inertial delay is. A transport delay transports whatever gets put into the wire. It's essentially just a wire. And it has a certain length, and that length kind of defines how long it takes to transport. Now, that's not entirely true, because what happens is in these big interconnect matrices on these FPGAs, there are transistor switches, and the transistor switch has to respond. So there is some delay in each one of these switches. And if you go through, 4 or 5 switches, besides the actual path length, which could be fractions of a nanosecond, the switches can actually create nanosecond delays. So the switches are pretty fast, but they're not instantaneous. And so we do have some transport delay, but glitches will typically these switches are fast enough typically to transport most glitches through without any problem. And notice here we put our delay before the target variable on the left-hand side of the equal sign, and here we put it just after the equal sign on the same side with the signals. So this is a transport delay of 5 nanoseconds, assuming we've defined our clock value as nanoseconds. And here, that's an inertial delay of 5, or propagation delay if you want. So you should just kind of memorize this now. It's pretty straightforward. The inertial delay on the left-hand side, propagation, transport delay on the right-hand side. And this is synonymous pretty much with propagation delay. This rejects pulses shorter than the 5 nanoseconds or whatever the value is here. This does not reject pulses shorter than the 5 nanoseconds. It propagates them. So here's an example. Z1 has a transport delay going to X, whereas Z2 has an inertial delay going, X has a transport delay going to Z1, and going to Z2, X has a propagation delay. Okay, so if X has a 10 nanosecond pulse, that should be transmitted because it's not smaller than this delay. And it doesn't make any difference here. So our Z1, we see a 10 nanosecond delay, and here's our pulse. And in Z2, we see the same thing. But here we have a little 2 nanosecond glitch. Z1 sees that because it's a transport delay, but Z2 does not see it because it's an inertial delay, and it filters out this 2 nanosecond pulse, which is shorter than the 10 nanosecond delay. So make sure you understand this. It's pretty straightforward. Okay, I'm gonna go ahead.
Can you go back to that, please?
Sure.
So if X pulses is 5 nanoseconds, in this case, Z2 would be clear all the time, 0?
It would, Z2, yeah. If the base state was 0, it would stay 0. Would not show that spike.
Okay, because it's only going up for 5 seconds, which is less than the propagation delay. So it's filtered out, correct?
No, because it's, yeah, right, yeah. Again, probably better to use the word transport delay, but yes, that's correct. They're pretty synonymous.
Okay, thank you.
All right. Any other questions? So we'll stop there. So hopefully everybody's, we'll finish up the first tutorial lab. And then I think there's a little worksheet at the end to turn in. Is that right? Has anybody done that? I think there is.
Yeah, there is.
Okay, so turn that in. But make sure you've demoed it to either Alex or John in lab, or if you didn't go to lab and you just did it at home, then shoot a little video with your ID in the video. Make it less than 60 seconds.
I don't think that there is a demo for the first one. They said that we didn't have to demo it.
Oh, okay, that's fine. Yeah, yeah, I think you're right now that I think about it. Yeah, that's fine. No demo for the first one then, so don't worry about it. No video, no demo.
I had to
Just,
demo it,
yeah, you don't, I mean, if you did, that's great. If you were in lab, you
but it
probably
doesn't
should.
matter. Okay.
Yeah, but they're not recording that apparently. Then that's fine. That's probably what I told them to do. All right. Any other questions? All right, make sure you do the homework. Make sure you turn in the lab sheet from the tutorial, and then you can be looking at the lab for next week. I might change it between now and next week, so just hold off on doing it till next week, till Monday or Tuesday or Wednesday, whenever your lab is. But if I make a change, I'll make it before Monday. I'll probably make it before Sunday. So I probably won't change it this week, but I might. So if you get way ahead, you run the risk of, maybe we might change the lab. Although I probably won't. I'll usually let you know, and I don't think I'll change this one, but I'm probably going to try and enhance a couple of labs. All right. Otherwise, then we will see you on Friday. I may have a video for you because it's just such a pain trying to go in. I need to be there for the micro lab at 10, and I just cannot do this Zoom thing from my office. I just don't have enough resources. It drives me crazy. So I'll probably have you do a video for Friday, and I'll either do a unique video or I'll have you watch one of the existing ones, but I'll tell you which one I want you to do. All right, we will talk to you later.